3.2c. 3.2c. What is a residual plot? What does it sound like it is? It is a plot of the residuals. It is a scatter plot of the residuals against the explanatory variable. So it's always going to kind of look like this, where you have like a graph where the x-axis is in the middle of the graph and you've got a positive and negative part of it. And so your residuals are on the y-axis. These are going to be your residuals. And then basically what you can do is kind of think about this as the least squares regression line flattened. That's kind of how it works. You'll see that in just a second. And so obviously we want small residuals. We want values that are pretty close to the line. We're going to have some that are positive, some that are negative, because of the fact that some of our residuals are above the line, or some of our data points are above the line, so we have positive residuals. Some of the data points are below the line, so we have negative residuals. And so this is kind of what a residual plot's going to look like. It's always going to have that vertical or horizontal axis straight out from the middle of the y-axis. And so here's the purpose of a residual plot, because the good news is you will never have to make one. You just have to look at it and interpret it. And so the whole purpose of a residual plot is to assess if the linear model is appropriate. That is the whole point of the residual plot. It is just to tell if the linear model is appropriate. Most of the time you can tell by looking at the scatter plot, because you'll be able to see if it looks like it's linear or if it's curved. But every once in a while, your data is maybe a little bit on the edge and you're not really sure if it's linear or not. A residual plot's going to really help you identify if something has a curved pattern or not. So here's how you end up interpreting it. If you have a curved pattern, if a curved pattern is seen, that means your linear model is not appropriate. Hopefully that should Hopefully that should make sense to you, because if you see a curve on the residual plot, then you are obviously not looking at something that is linear. You're looking at something that is curved. Maybe it's quadratic or logarithmic or exponential. None of that matters, but you just know that it's not linear. So if you see a curved pattern, the linear model is not really the best fit. Another thing you need to be careful of, if a megaphone pattern is seen, you guys all know what a megaphone is, right? Okay, it's small and then it gets bigger, right? If a megaphone pattern is seen, use caution when using linear model. If you see a megaphone pattern, you gotta use caution when you use the linear model. And here's why. Let's say this is your residual plot, and you have a graph that looks something like this. There you go. There's a megaphone pattern for anyone who doesn't know what a megaphone pattern looks like. There's a megaphone pattern. So again, these are residuals. These are the actual y value versus the predicted y value. This is basically the distance from the data to the line. On the left side, these are making pretty good predictions. Our residuals are pretty small. But then our residuals get really big. And that kind of indicates that our linear model doesn't really hold up when our X value gets large. And so these residuals are very large on both the positive and the negative side. And so that just tells us that we need to be cautious about using the linear model because it might not be doing a very good job of making a prediction on the higher end. Okay, so you literally can just say there's a megaphone pattern, use caution. Not saying the linear model's terrible, it's just not going to be the best for those big values of X. Okay, so here's kind of how it comes about. So on the left here, you have a scatter plot. You have the least squares regression line going through it. And we've talked about what a residual is. We've talked about that a residual is basically the distance from the data values to the line, right? So these are all your residuals. It's the distance here. And so small distances mean that your data is very close to the line and your predictions are going to be pretty good. Big values like this one mean that your prediction's going to be kind of far off, okay? So what we basically do is we take that line and we flatten it. And all the data stays in the same kind of pattern, but it just kind of reshapes so that you can then see how big the residual is on the residual plot. So these two down here on the bottom left, you can see that they are the same distance from the line. Those are the same distance from the line. Those correspond to those dots on the residual plot. Again, they're the same distance from the line. And so their residual is somewhere around negative 0.5. So this is negative 0.5. This is also negative 0.5 as far as the difference. If I take y minus y hat, I would get negative 0.5 for each of these, similar to how this shows that the residual is negative 0.5. All right, the top three up here, if you see these top three right here, correspond to these three. So they kind of stay in the same pattern. They just kind of rotate a little bit. And you can see that those have a pretty big residual, which makes sense because these are pretty far from the line as compared to these guys down here. So that's kind of how a residual plot works. When I look at this one, do you guys see a curved pattern of any kind on this one on the right? No. Not really. There's maybe a slight megaphone thing going on, maybe. But for the most part, this is a pretty good linear model. And our residuals are anything from positive 2 to negative 2. That's a pretty small residual, okay? Think about the Skittles. Skittles had a residual of negative 96. That was a huge residual. That value was really far from the line. These guys are pretty close to the line. So you look at your y-axis and you can say, my residuals are pretty small here. So this linear model looks like it's a pretty good deal, all right? We could also look at the strength, the R value, and that could help us decide if this linear model is a very good fit. And then later this week, we'll talk about another value that can help you determine if your linear model is a good fit or not. So that is kind of the basics of a residual plot. Here's another one on the next page. Again, we have our scatter plot with our least squares regression line on the left. And we can turn that into a residual plot. If you look at these three dots right here, you can see that the pattern basically holds up, okay? We're just kind of rotating this graph around a little bit. Our residuals, again, pretty small. This goes from like positive 6 all the way down to like negative 4. So our residuals are a little bigger from the previous one, but for the most part, still pretty reasonable. When you look at this residual plot, do you guys see a curved pattern? Do you see a curved pattern here? Not really. So the linear model would be appropriate for this one as well. All right. Cool. Next, We're going to look at these graphs and decide if the linear model is appropriate or not. First one, far left, plot A. What do you guys think? Is the linear model appropriate?
No.
Why not? What's wrong? Do you see a curve pattern? You do not see a curve pattern. So if you don't see a curve pattern, then your linear model is probably doing an okay job. It's doing the best it can with the data it's given. Yes, these residuals are kind of big, but the linear model's doing a good job. There's not a curved pattern that I have to worry about, not really a megaphone either. So this one, the linear model is probably appropriate. So for plot A, linear model is appropriate. All right, let's look at plot B. Do you guys see a curved pattern? Oh, yeah, you do. So is the linear model appropriate? No, not even a little. Linear model, not appropriate. All right, what about plot C? Curve pattern? Yeah, I mean, don't look at too detailed. Yeah, not really a curve pattern there. The residuals are pretty small as well. Yeah, so linear model is really good here. Linear model is appropriate. And then that final one there, what do you see? You got a little megaphone there. So again, linear model might not be the best when your X values are getting big, but it's probably okay. So we would say use caution with linear model because of megaphone pattern. So you can use caution on that one because you've got a little bit of a megaphone pattern there, so you want to be a little bit careful. So again, you never have to make a residual plot. You just have to look at them. If you see a curve pattern, you kind of go, I don't think that's a good linear model. Or yes, that model is perfectly fine. Go for it. All right. So I want to show you guys something real quick. All right, here is a graph, a scatter plot. That is, it's pretty strong. It's got a pretty strong correlation. Okay, I'm going to add the least squares regression line here. Boom, there it is. Now, think about and visualize this line getting flat, and then these dots just kind of rotating with it. Would you see a curved pattern in the residual plot? Very much so. A lot of times you can see the curve pattern even on the scatter plot, but we check the residual plot just to be sure because it will over-exaggerate any curve pattern that might exist. So this one would obviously not be a good linear model, which you probably would have known that anyway. So I want to show you one more thing here about the least squares regression line. There is a very important point that is always on the least squares regression line. If I take every single one of these X values, every single dot's X value, and I average it, and then I take every single dot's Y value and I average it, that becomes the tipping point for the middle of the line. It is the point where X, the average X and the average Y value is. So that's the point that this is going through right here. The average X's and the average Y's will always go through the least squares regression line, or vice versa. Even if I add dots that move the line, I can see that it will still go through the average X and average Y coordinate. So that where that crosshair is there, that is the average x and average y. As I'm adding more x's and y's that have to be averaged in, it is moving the line all over the place, but it's always keeping the average x and the average y right in the middle of the line. And so that is always true. Your average x and average y value will always be on the line of best fit, the least squares regression line. So let's make sure we write that down real quick. So a very important property of the least squares regression line, the LSRL, always contains the point x bar, comma, y bar. Again, x bar is your average x value. Y bar is your average y value. So I average all those x's, I average all those y's, and that becomes the middle of your least squares regression line. And that point is always on the line. So, for those of you that are keeping up, y hat equals a plus bx. That means that if I plug in y bar, what should x equal? X bar. That is absolutely going to happen every time because the point x bar, y bar is on the line. Same thing, and that works vice versa. If I plug in x bar, I will get y bar. Whatever I plug in, if I plug in x bar, I'm going to get y bar. If I plug in y bar, I'm going to get x bar. They go back and forth that way. Do you guys have any questions about that property of the least squares regression line? No. All good? Okie dokie. So the last thing I want to talk to you guys about today is something called influential points. Influential points. An influential point in regression is any point that, if removed, changes the relationship substantially. Examples include maybe it gives a much different slope. Maybe if I remove a point and it all of a sudden moves the slope of the line considerably, that would obviously be an influential point. If it changes the y-intercept considerably, that's going to be influential. Or it changes the correlation considerably, that's going to be influential. Now, there are two types of influential points, okay? Kind of like you could say, there are two genders, right? Male and female. Well, there's two influential points. There's going to be one is going to be called an outlier. The other one is going to be called a high leverage point. They are both influential points. It just depends on what kind of influential point it is. So your first one here is outlier. An outlier in regression is a point that does not follow the trend of the data. It does not follow the trend of the data. And it's going to have a large residual. That's going to be an outlier. Usually it's very clear when you have an outlier. It's very far away from the line. It's going to change things. If you were to remove that outlier, it's going to change your slope of your line. It's going to definitely change your correlation, all that kind of stuff. A high leverage point in regression has a substantially larger or smaller x value than the other observations have, but here's the difference. These are in the trend of the LSRL. So they're kind of far away from the rest of the data, but they're kind of close to the line. They're just really far away, but in the same pattern or in the same linear path, if you will. So those are going to be called high leverage points. All right, so I want to show you guys a few examples here real quick. before we do the ones that are on our page here. So these are pretty similar. Okay, so here's our scatter plot right here, okay? Here's our least squares regression line. What point is on the least squares regression line? X bar, Y bar, right? So there's my X bar, Y bar. Okay, cool. All right, so I want you guys to think about this as the y-intercept. I'm not saying this is the y-intercept, but I want you guys to kind of think about this right here is your y-intercept, okay? And I'm going to add some dots to see what happens. We're going to notate what happens with the correlation and also with the slope of the line, okay? So we're going to think about this point as the y-intercept. We got our slope is how steep the line is, and then we got our correlation right here. All right, I'm going to add a dot way down here on the bottom right. What do you think is going to happen to the slope of the line? It's going to get less. It's going to tip down because it's trying to compensate for that dot down there. What does that mean is going to happen to this y-intercept? It's going to go up. If this line tips down, then this is going to go up, very likely. What's going to happen to the strength of the correlation if I put a dot way down here? It's going to get weaker. Let's see if all those things happen. Here we go. Boom. Oh my gosh, that tipped the line a ton. Right? It did a whole flip. It changed it to negative. So that one little point. Now, is that point an outlier or is that point a high leverage point? This is an outlier, okay? It is not in the trend of the data, and it is far away from the rest of the data in the x or in the y direction. So it's far from the line. It is very much changing the slope. It's changing the y-intercept, and it's changing the correlation. It's changing everything. All right, I'm going to put a dot way up here. I'm going to put a dot way up here, very close to the line. What is going to happen to the slope of the line if I put a dot right up here by the line? Not much is going to happen. What's going to happen to the y-intercept? Not much is going to happen. What's going to happen to the correlation? It's going to get stronger. Watch this. That one dot made my correlation stronger because basically what that says is that this linear model wasn't only good here, it actually was good way up here, so that linear model holds up over time. Very different than our soda can example, right? That linear model leveled out at 355 milliliters of soda because that's what we started with. This one holds up all the way over there, so that correlation gets stronger. Does this make sense? Okay, cool. What if I put a dot up here? Actually, I'm going to show you guys one other thing here. All right, so here's the X bar, Y bar. This is the average X and the average Y. What if I put a dot up here, right along the average X value? So I put it right here. What's going to happen to the line?
It's going to go that way.
It's going to go this way?
Yeah.
You think? Yeah. Let's see. So all it does is it shifts the line up. So does that mean the slope changes? No. Does the y-intercept change?
Yeah.
A little bit. It shifts up, right? What about the correlation? Gets weaker, okay? What if I were to put a dot over here in the y direction? What's going to happen to the line? It's actually going to shift over if I do it right. Let's see if I can get it right on there. Now.
See, that's what I was thinking.
Maybe it's because it's too far away. Actually, it is because it's too far away. You're right. My bad. It's because of how steep I have this line. So sometimes it will, sometimes it will just shift it over. It's probably because I don't have this like this. Okay, there we go. Now, no.
You have to put it on the line.
I'm trying there, bud. See, like So, okay, this only works in the X direction.
Wait, what if you put more dots like all the way up the line?
All the way up the line? Let's see what happens. I love that you're asking here. Like this. Now let's see what happens. It still tips a little bit, but not as much. So, you see how it kind of depends on what's going on with your scatter plot. But you guys are doing really good in thinking about what is happening. So, great job on that. Obviously, something really far down here is going to definitely tip the line. Something way over here changes the line. Things like that. Okay, so let's go back to our example on our notes, our examples here. So our first one here. What do you guys think about that green dot? The green dot is the top right dot. Do you guys think that that is an outlier or a high leverage point?
High leverage point.
That is a high leverage point. Very good. Now, let's think about what would happen if I removed that. What would happen to the slope of the line?
It would get a weaker strength.
Not much would happen to the slope. What would happen to the y-intercept? Probably not much, but what would happen to the correlation? It would get weaker. Very good. So, slope, I know you were, I'm so excited. Slope and y-intercept unchanged. Correlation gets weaker. Now, obviously, that's me talking about removing the dot. If I were to say what happened when I added the dot, what happened to the correlation when I added that dot? It got stronger. Okay, just want to make sure. All right, cool. Here's this one. I've got a dot that's down here, probably pretty close to the average-ish, but I don't know. We'll see. What happens if I remove this? Or I'm sorry, first of all, is it high leverage or outlier? This is an outlier. It is outside of the trend of the data, and it is far away from the line. It's got a big residual. So what do you think would happen if I take this guy away? What's going to happen to that line? It'll go up like this a little bit. Okay, so the slope might increase some. So what does that mean is going to happen to the y-intercept here? It's going to go down some, okay? And what's going to happen to the correlation? It's going to get stronger. Very good. So our slope increases. Y-intercept decreases. And correlation gets stronger. Again, that is if I take that point away. If I were to add it, then it would get stronger. Very good, very good. All right, let's look at this last one here. We kind of saw this one. I kind of showed you guys a little bit of what this one will look like on that little applet. So what's, first of all, is this an outlier or high leverage?
Outlier.
Totally an outlier. What's going to happen if I remove that dot? What's going to happen to the slope? It's going to increase. What's going to happen?
Y-intercept's going to go down.
Y-intercept's going to go down.
And it's going to get a stronger correlation.
Good. Slope increases. Y-intercept decreases. Correlation gets stronger. Very good. All right, last question here. This is from an AP exam from a few years ago. The scatter plot of student height in inches versus corresponding arm span length in inches is shown below. One of the points on the graph is labeled A. If the point is removed, then what would happen? I'm going to give you guys a couple of seconds here to figure out which one you think it is. All right, on the count of 3, tell me what you think. 1, 2, 3. C. You are absolutely correct. The slope of this is going to increase if I take that away. The correlation's going to get stronger. Even the y-intercept, what would happen to the y-intercept? That would decrease. Very good, very good, very good. Questions?